Welcome to this lesson on oscillations. Today, we'll explore two important concepts in physics: damped oscillations and forced oscillations with resonance. These concepts help us understand how objects vibrate in the real world, such as shock absorbers in cars, bridges in the wind, or even atoms in molecules. Let's start by quickly reviewing simple harmonic motion before adding complexity with damping and forcing. Simple harmonic motion occurs when a restoring force is proportional to displacement. For a spring mass system, this is described by Hooke's law. F equals k times x, where k is the spring constant. The solution to this equation gives us sinusoidal motion x equals a times cosine of omega times t plus phi, where omega equals the square root of k over m, the natural angular frequency of the system. Now, let's add damping to our system. In real life, oscillations don't continue forever. Damping occurs when a force proportional to velocity opposes the motion. F sub d equals negative b times v, where b is the damping constant. Our equation of motion now becomes m times the second derivative of x plus b times the first derivative of x plus k times x equals 0. The solution is a decaying oscillation x equals a times e to the power of negative b over 2m times t times cosine of omega prime times t plus phi, where omega prime is the damped angular frequency. Omega prime equals the square root of k over m minus b squared over 4m squared. There are three important types of damping, depending on the value of b. When b is less than 2 times the square root of k times m, we have underdamping. The system oscillates with decreasing amplitude. This is the case we just saw. When b equals 2 times the square root of k times m, we have critical damping. The system returns to equilibrium as quickly as possible without oscillating. When b is greater than 2 times the square root of k times m, we have overdamping. The system returns to equilibrium without oscillating, but takes longer than critical damping. Let's summarize the mathematical conditions for the three types of damping. 1. Underdamping, b less than 2 times the square root of k times m2. Critical damping, b equals 2 times the square root of k times m3. Overdamping, b greater than 2 times the square root of k times m. These conditions determine whether the system oscillates while returning to equilibrium. Now, let's add an external driving force to our damped system. This creates what we call forced or driven oscillations. Imagine pushing a child on a swing. You're applying a periodic force to keep the oscillation going. Our equation now becomes m times the second derivative of x plus b times the first derivative of x plus k times x equals f sub max times cosine of omega sub d times t, where omega sub d is the angular frequency of the driving force. After initial transients die out, the system oscillates at the driving frequency omega sub d, with an amplitude given by a equals f sub max divided by the square root of the quantity, k minus m times omega sub d squared plus b squared times omega sub d squared. One of the most fascinating phenomena in forced oscillations is resonance. Resonance occurs when the driving frequency omega sub d approaches the natural frequency omega sub 0 of the system. Looking at our amplitude equation, a equals f sub max divided by the square root of the quantity, k minus m times omega sub d squared plus b squared times omega sub d squared, we can see that when omega sub d approaches omega sub 0, which is the square root of k over m, the first term in the denominator approaches 0, potentially leading to a very large amplitude. The amplitude versus frequency relationship creates what we call a resonance curve. The peak of this curve occurs near the natural frequency of the system. The amount of damping affects the shape of this curve. Low damping gives a sharp, high peak. High damping gives a lower, broader peak. Resonance has many practical applications and can be observed in various real-world scenarios. For instance, a child on a swing, parents push at just the right frequency to achieve maximum height. Musical instruments, string and wind instruments operate based on resonant frequencies. Radio tuning circuits are designed to resonate at particular frequencies. Resonance can also be dangerous. The famous Tacoma Narrows Bridge collapse in 1940 was partly due to wind creating resonance with the bridge's natural frequency. In engineering, we often want to avoid resonance by 1. Changing the natural frequency of the system. 2. Adding damping to reduce resonant amplitudes. 3. Isolating systems from driving forces that match their natural frequencies. Let's summarize what we've learned. 1. Damped oscillations occur when a resistive force proportional to velocity is present too. There are three types of damping: underdamping, critical damping, and overdamping 3. Forced oscillations happen when an external periodic force drives the system 4. Resonance occurs when the driving frequency matches the natural frequency of the system 5. The amount of damping affects the height and width of the resonance peak. The key equations to remember are: for damped oscillations, x equals a times e to the power of negative b over 2m times t times cosine of omega prime times t plus phi. For forced oscillations, a equals f sub max divided by the square root of the quantity, k minus m times omega sub d squared. Squared plus b squared times omega sub d squared. Understanding these concepts helps us analyze and design oscillating systems in physics and engineering. Thanks for watching.